Okay, it's being a little bit weird, but that's all right. So good morning. What we are going to do today is do some additional watershed modeling with WMS. We're going to review the process that you go through to delineate the watershed. I'm going to show you some additional tools, and we'll start our first modeling activity where we're actually using the rational method to figure out the runoff characteristics for a watershed in Ona, West Virginia. As a reminder, your first WMS related assignment is due on Monday, and so you've got the weekend to work through that. You may have already got started on it. You know, the demo that we did in Wednesday's class meeting addressed most of the questions on there. I was looking back through it, and I think there's one additional kind of skill that I need to show you how to do today, and that's trimming a digital elevation model. So that will be one of the things that I show you today. Before we begin with the demo, are there any questions or any concerns based on your use of the program on Wednesday? All right. So if there aren't any questions, just again, I encourage you to go ahead and unmute your microphone and ask a question, or if you'd rather type one in, that's okay too. But I've got two screens today, so I'll be able to keep tabs on the Collaborate view while we're also working through the program. So here's the list of activities that we're going to do today. We are going to identify the watershed, and that's where I've said before sometimes it can be tricky finding just from street descriptions the watershed and making sure that the entirety of the contributing areas is included in the data that you download. So that's a skill in and of itself. We will obtain the digital elevation model, delineate the watershed by computing topaz, dropping the outlet in the appropriate spot, and then we're going to apply the rational method. And so I'm going to show you some of the sub-tools that are inside of the WMS, and one of them, the hydrologic modeling module, is what allows us to tell the program which watershed model we're choosing to use. And then along the way there's just some side skills that you'll learn, like how to look up the background information that WMS uses. We'll check out the help button because it takes you to the product documentation that can be used, and we'll break the watershed up into sub-basins rather than treating it just as one basin all by itself, and trim the DEM. Okay, so we're going to do this with a watershed that's in Ona, West Virginia, and there's a culvert we'll assume needs to be replaced, and it's a pretty good assumption, by the way, assuming that a culvert needs to be replaced in West Virginia. We're going to take a look at the intersection of Blue Sulphur Road and Lichens Branch. There is a stream that comes in to a larger stream, and we're going to delineate the watershed there, and we're going to do a sensitivity analysis to try and find out what would be the runoff from that watershed for a couple of different C values. Okay, so let's toggle over to WMS, and in the program we're going to start by activating the wizard, the hydrologic modeling wizard. And I've already kind of pulled up the location, but I guess maybe since you don't necessarily know where it is, let's begin with that. Let me start by pulling up Google Maps just so that we begin with an idea of where that road is. And so Lichens Branch Road in Ona, West Virginia. Alright, so the description that we have is that we're looking for the intersection of Lichens Branch and Blue Sulphur Road, and there you see it. So Lichens Branch isn't too long. We can find the end of it. It is here. And so we're looking for, there's going to be a stream that runs along Lichens Branch, and then it junctions in at Little Cabell Creek. And so we're trying to figure out how big is the watershed that's upstream of this junction. So now if we just kind of, for perspective, zoom out a little bit, we can see here's the interstate. So Blue Sulphur Road goes under the interstate, and then we're looking for this junction with Likens Branch. Alright, so with that perspective, we can now switch back to WMS, and in the wizard we have to begin by identifying a location we're going to save our project. And so if you haven't already, create a subfolder for today's demonstration. So this is my class demo for Friday. Give it a file name, and then you have to click save. Oh, by the way, let's see. I got the suggestion. Yeah, check that out. Now you can't see the cursor, but I can gesture at spots on the screen thanks to a great suggestion that I got from, I think James told me that there's this target thing. So I'm just going to be constantly doing that all through today's lecture just to show off that I have this new cursor. So you have to click save, and if you don't, then look up here. Right now it's untitled. Even though I typed in the name yet, it's not until I click save that now that title is visible up in the top of the screen. Okay, so now that it's saved, it's kind of established the file name, this fridaydemo.wms. There's not much in that fridaydemo.wms file yet, but that's where the digital elevation model is going to be embedded once we download it. So you click next, and we have to make sure that we've defined our projection. Yours may not still be there from last time, and so let's choose as the projection. It'll bring up the greatest hits. If you click on set projection, it'll bring up the most recent ones that you've used. We'll use one of the available projections, but making sure that we set it to UTM zone 17. Okay, so click on that, and then project boundary. We have to define the project boundary. So click on define, and yours will probably set to the Darnell Road, which is where we were working last time. You know, in our previous example from the last class, we were over in this part of Huntington. So if you type in Ona, West Virginia, and jump to location, it'll take you to the center of the bustling metropolis. But we need to back out a little bit because Blue Sulphur Road is to the west of downtown Ona. So here's Blue Sulphur Road. We're following it up, and there's Likens Branch. Likens Branch. Alright, so now remember that if we're zoomed out too far, we'll definitely get all of the elevation data we need, but we're actually going to be downloading too much, and it takes a long time to get that data and a long time to process it, and then it's hard to find the crossing that you're interested in. So it's good to only get the amount that you need, but not too much. And so, like if I'm zoomed in too close, we can kind of tell from the shading of these ridge lines that I don't have the entire watershed. If I just click OK here, I'm going to have that long line across the top that indicates I haven't obtained all of the data that I need. So I'll zoom out a little bit. That might be all of it. My guess is that our watershed is up in this ridge line, across the top here, up to there. This is an odd spot here. Like maybe just to be safe, I'm going to back out a little bit more. Okay, so we're going to get plenty of elevation data here. I think we definitely have got it all at this view. So get something similar to what you see on screen, and then click OK. Oh, it looks like my wizard is back in the background, so I have to click on WMS again, and then that brings it back to the forefront if the same thing happens to you. So in the wizard step, we just defined our bounds, and now we have all of the coordinates set that encompass the area we're interested in. I'm going to click next. Make sure that the web services is checked yes, and then click next. Alright, now looking at which options are on the screen there, I'm just going to have it get the street map and the worldwide elevation data. just for now, just limiting it to those two things. And so then click on download data from web and use the default OK settings for the resolution that it goes and downloads for the image, and then this one is for the DEM file. So zoom level 13 means that each of the cells, each of the elevation cells that are displayed have a width and a height of 15 meters. So we click OK for that, and then it's downloading it. Down here in the lower left, it'll kind of give you in red the progress as it's beginning to download. So let's close the wizard for now and look at what we've got. We've got kind of the useless, goofy elevation map that I'm going to turn off here because I don't want it to obscure the street map that's in the background. So I'm also going to turn off these elevation contours for just a moment, and you can see here's Lichens Branch intersecting Blue Sulphur. So if I zoom in, you'll notice that it's kind of pixelated. I mean, it just doesn't look fantastic. I can pan side to side a little bit. A word about imaging. Now what it's done is it's got this street map and it's saved. If I click save right now, just a word about file structures, let's pull up and look at in that subfolder that I'm working in, what are some of the other let's see, WMS, Friday, ONA, and I think I'm in class demo. So here are the files that exist in that project folder that I'm working in. And so it's got the .wms file. So this .wms file is right now 831 kilobytes, so it's pretty small, but that's where the digital elevation model is embedded. It's embedded in there. The TIF, that's an image file, so the elevation data and the street map, it's kind of the raw image file, and then the TFW is called a world file, and that's what you can see. It's very small. You could open that with a notepad and it just defines the coordinates, and so it's kind of geo-referencing those image files so that they pull in the correct spot. So if we want better mapping, one of the ways to get better mapping, if we turn that off and then go to Get Online Maps, I'll click World Street Map and click OK, and so now the World Street Map that it's bringing in, it just kind of is like the difference between downloading an audio file and streaming the audio file. This World Street Map that's over here on the left side in the GIS data, if I zoom in, it's going to continue to download and get the finest version of the image file you can. So it's kind of on the fly, going to be updating, and it's a little bit slower. You'll notice that it takes some time for it to on the fly download the data file, and so it's kind of a balance between, do you want to download and permanently keep the mapping data, or do you want to have the streaming version? Okay, so just for now, let's turn on the elevation contours, and we're at the step in the wizard where if you bring that back to the forefront, we've downloaded the data and we need to compute topaz because we have the elevations, but we don't have the blue lines that indicate where the streams are going to be, those flow accumulation cells. So click on Compute Topaz, and what we should see is that it puts those blue lines alongside the road on Lichens Branch. So let me close this and zoom back in on where I'm interested in. So here's Lichens Branch, and so the intersection of Lichens Branch and Blue Sulphur. And so if I turn the elevation model back on, you can see that yes, in fact, there is a creek that's matching up with Blue Sulphur. And so we want to drop the outlet at our area of interest. And so back to the hydrologic modeling module and choose outlet location. So click on Create Outlet Point, and then make sure that you have it upstream of the junction. If you put it right on the junction of the two, then it's going to include the upstream areas as well. So I'm going to put it here in this location. Alright, and then in the next screen we're going to delineate watershed.
Dr. Wade,
Yes.
something wrong. I don't have the, what was it, come on here, computing the topaz, but it didn't change.
Can you say that again, please?
I was trying to compute the topaz,
Okay.
but it didn't change.
Okay, so do you have the digital elevation model? Like over here on the left side, did you download the data?
Yes. Oh,
Okay.
I gotta reselect that and then compute it?
No, as long as it's there, it should work. It doesn't necessarily have to be turned on, I don't think. But just in case, turn on the elevation data over on the left side. And so when you click Compute Topaz, are you seeing the blue flow accumulation cells now?
Hold on. No, it has changed.
When you say it didn't change, what do you mean?
Wait, I'm good, man.
All right. Sounds like you've got it.
Never mind. Different button.
Okay. So after you compute topaz, then you need to create the outlet. So you're just dropping the outlet a couple of elevation cells upstream of the junction. So pick a spot that is not at the junction, picking a couple of blocks away, create the outlet point, and then on the next screen click on Delineate Watershed. So does everyone else have this watershed of about 260 acres? Cody, Logan, are you both with me? Logan's got it. Good. Okay. So we've delineated the watershed. Now let's apply the rational method. So across the top there are different modules that correspond to which tools you want to have available and what you're going to be doing with the data that's on the screen right now. And you'll notice that right now we're in the terrain data module. And when you're working through the wizard, it just kind of takes you to whichever module you happen to need, and then the tools will become available. But you don't always have to work in the context of the wizard. You can jump around and kind of manually decide your workflow. And so let's do that now. Let's go into the hydrologic modeling module by clicking on this button. And you'll notice that the menu structure changed over here on the left side of the screen. When I was in the terrain data module, it was saying like TEI, TIN, DEM, flood, and so on. But when I changed to the hydrologic modeling module, then the menu structure changes, and also the tools that are over on the left side of the screen, those are different as well. One thing I want to draw your attention to is this drop-down box where it says Model. We're going to be using not the HEC1 model, but right now we're going to choose the rational method. So in the drop-down box, we're in the hydrologic modeling module and choose the rational method in the drop-down box. And then we want to bring up the characteristics of the rational method. And for some reason it's kind of a little bit annoying. They put the labels and some of the data on top of itself. So use this select basin tool, click that, and then click on the brown, let's see, yeah, there we go. I moved the label out of the way. So just click on the basin symbol, just click and drag it so that it's not right on top of the area description. And now if you double click on it, it brings up some information having to do with the rational method. Alright. And Another way that you can get that same window open is on the menu structure across the top here. Click Rational Method, Run Simulation, and it brings up that menu. So you can either double click on the symbol or go through the menu. And so now that we're in the rational method, we see some of the information that's familiar to us. You know, Q, the flow rate, is CIA. And so that's the essence of the rational method, is that you have to assign some C value to your watershed, have to have input rainfall data and the area, and that's how you get the flow rate. So Q equals CIA. And there's some nice things that are built into WMS that make it easier for us to apply the rational method. The first thing that it's nice that it's doing is it's automatically calculating the area for us, and it's doing it very accurately. So you'll notice it has the units here, 262.6 acres. Now it's not going to calculate the C value for us. We have to have that information, and in the assumptions we're going to look at 3 different C values. So we're going to look at a C value of 0.6, 0.65, and 0.7. So let's begin by just putting in 0.6 as the C value. The time of concentration and the rainfall, we can have it compute for us. And so click on Compute for the IDF curve, and it brings up data that has to do with rainfall intensity. And you know, if I ask you what's the rainfall intensity for a 5-year storm, for a 10-year storm, and so on for this location, probably you'd go to the Precipitation Data Frequency Server. That's the NOAA website where you can just click a point on the map and it gives you all the rainfall data that you could want. That's what this is going to do. It's going to, in the background, go to that database and obtain the rainfall data for our location. But before it does that, it wants to have some information related to the time of concentration. So let's begin with that, because remember that the worst case scenario for rainfall intensity is that the storm duration is equal to the time of concentration. That's what's going to produce the biggest peak runoff, is if your intensity just is exactly equal to the intensity that corresponds to the time of concentration. So the program has calculated our average watershed slope. It's calculated the length, the flow path length, and it doesn't know the Manning's end though. So just to start to get a feel for our time of concentration, let's calculate a pretty typical Manning, let's use a pretty typical Manning's end of 0.03 for the n value, and then click on Compute TC instead of the specified. So we're going to have it calculate a time of concentration if the water was flowing through a channel that had a roughness of 0.3, and then it had this length, and then the average slope of the channel 0.33. Now that's maybe the average slope in our watershed, but that's not going to be the average slope once the water begins to be channelized. But we're just going to look and see what time would that give us. And so if you click intensity, compute intensity, oops, sorry, we have to define that. Let's use the 10-year IDF curve. So you click on that row and then compute intensity. All right. I think it can. All right. Well, it doesn't want to do it based on the channel data. Let's go to pick the. Okay. Click on the basin data, and instead of time of concentration in this drop-down menu, if the default is lag time, change it over to time of concentration. Your default was probably lag time. And then in the drop-down box, go to the SCS method. So the SCS method of lag time, and let's use a typical runoff curve number of 75 for this area, just to get a first time of concentration. So now we have a time of concentration estimated of 25 minutes. I wonder if we have to do that one first before it will calculate the overland flow version. So that's with the calculator that we just did here in the basin data. It has now filled in an estimate of the time of concentration of 25 minutes here, and now it will go and get our Boy, this is so odd. Yesterday, as I was preparing for this, it was definitely, I wonder if maybe the web connection isn't working to our rainfall intensity data. Oh, get online data? Yeah. I was clicking on the wrong button the whole time. Click get online data here, and compute intensity once it has the online data. Alright, so it's a two-step process. Get online data goes to the precipitation data frequency server, and it finds the 5-minute, 10-minute, 15-minute, 30-minute, and then when you click intensity, it's interpolating. So it's saying, for example, since our time of concentration is essentially 25 minutes, it's doing a linear interpolation between the 15-minute storm and the 30-minute storm. So we have an intensity of 3.2 inches per hour, which you can see is between the 4.2, 2.9. Alright, so now I'm wondering, now that I've clicked get online data, if it would allow me to do the compute TC where we had the assumed Manning's N value. So now click compute intensity with that, and yeah, alright, so it's got a different intensity than we had before. So the specified time of concentration is going to be 1 rainfall intensity, just based on Manning's equation gives you another, and so there's a couple of different options, and you can choose the one that's more conservative. So just to back up, what I'd like you to do is try to go through the process of calculating the flow rate for our basin using the runoff coefficient of 0.6, 0.65, and 0.7. And so you can see that right now it's computed the runoff of 665 CFS for the area, the rainfall intensity, and the runoff coefficient that we have of 0.6. But see, how does that flow rate change for the other C values as well? Okay, so what you'll notice is that when you change the C value, it automatically updates the flow rate. So if I have 0.6 and change it to 0.65, as soon as I input that, it now changed the flow rate to 720 CFS. And if I change it to 0.7, it's dynamically on the fly changing the flow rate to the increased amount. So there's like kind of two levels of sensitivity. We can see how does the model change based on the C value, but then we can also double check to see how does the model change based on our time of concentration? Because I was using the time of concentration that was associated with the 16 minutes, but what about back to using the basin data and the SCS method? So this longer time of concentration, for this longer time of concentration, then that's going to change the rainfall to the lower intensity, and so now we're using the lower I, and then the flow rate for that, if we're using 0.7, and the lower intensity would be about 600 CFS. So that gives you an idea that the envelope of possibilities it can be. If you click on this button, Compute Hydrographs, and just accept the default option here, then what it does is down on the screen, if you close this rational method window, it's created a hydrograph that is triangular. It just goes straight up to the peak flow, and it happens in the time of concentration. So the time to peak is 25 minutes. It goes up to 600 CFS, and for a storm where the rainfall intensity is constant and then immediately stops, then the trailing leg of the hydrograph goes back to 0 in the same duration. So they're calculating the volume, the area under the curve that's associated with the volume of flow during the storm. Okay, so that's how we could do this with a single delineated watershed. Now, if we open back up the rational method window here, I want to show you, it doesn't know which watershed we have selected, so double click this. If you click on the help button, then it brings up the product documentation for WMS, and the nice thing about it is it can give you some background information on how the program is running and what are some of the assumptions associated with each. And so here it's telling you, Q equals CIA and the units factor that would be used. If we are, let's see, in the T sub C methods, if you click on help, it will bring up the different time of concentration options, and so you could look at learn more information about the units that are used for the time of concentration methods, so that can be useful. You can look about the IDF curves and how it gets the rainfall data and which database it's connecting to. So don't be afraid to access the help menu in WMS, because it'll just help you to know the connection between the theory and the application. So we've been doing this with our watershed is 262 acres, and in the product documentation for WMS it mentions that you typically want to limit the limit your modeling of a single watershed to 1 square mile, so 640 acres, and frankly the rational method does better the smaller the watershed. If you're doing a watershed that's 640 acres, then you can expect quite a lot of error. And so one of the things that we can do is we can put in additional sub-basins and break this big single watershed up into multiple smaller watersheds. And so let's do that by again starting up the wizard and stepping ahead to choose outlet locations. What we're going to do is we're going to break it up into 3 segments. Right now there's an outlet just at the main crossing where one stream is joining the other. But let's also add additional outlets at this location and at this location and see what effect that has. And so click on the button for Create Outlet Point. So I'm going to click Create Outlet, and then I'm going to be dropping that outlet here. There's one, and then another create outlet. Let me just move it off to the side. Doing it here. Okay. And click next and delineate watershed. And it'll give us a warning message that it's going to delete the previous boundary of what the watershed was, because we had just one big basin, but now it's going to delete that and it's going to create 3 separate smaller sub-basins. And so we tell it that that's okay, and it goes through the process of calculating. And if I close this, you can see that now what was a single watershed has been subdivided into 3 different sub-basins. And just because it can get a little confusing to have the network symbology on the screen there, you know, like it's creating kind of a schematic of our watershed. These brown boxes represent the basins, the yellow circles are the outlets to the basins, but you'll notice it's subdivided the watershed up into one that's about 99 acres, another one that's 99 acres, and then the remainder here, if I just drag that symbol out of the way so I can see, 65 acres. So that's how you would subdivide a watershed. And if we want to do the modeling for that, we can open up the rational method and run simulation, and this time it's only displaying the basin that we have selected right now, but you can also have it do show all basins, and now it's got each of the 3 basins, the one that's 99 acres, one that's 99.55 acres, and then the one that's 65 acres. And so you could, if you knew that one of these basins had more urbanization in it, for example, you would be able to have a little bit more resolution. So let's say, for example, that both of these outlying watersheds have a lower curve number, and so let's assign them 0.6, 0.6, but then we know that there's more houses in the one that's closer to the junction of blue sulfur, so maybe that would be a watershed that has 0.7 is the runoff coefficient for that particular sub-basin. And then let's compute the IDF curve, and if we, it still has the data in the background because we've defined the location, so it's not going to find a different spot for us. Let's try using the 0.03 for the Manning's equation and compute intensity. So it's going to be basing this time of concentration on Manning's equation and the travel time that it would take for water to flow through a channel of this characteristic. And so it computes the intensity for that sub-basin, and if we want to compare, so that's saying 5.03 inches. So it's putting the intensity into the equation just for that sub-basin, but we could go back into the basin data tool and we could check using any of these other methods that are available for time of concentration and lag time. One that I often like to use is the SCS method, and we would have to use a typical curve number for the area, 75, and it estimates a different rainfall intensity with that. Oh, did it not copy over the specified value? So for the SCS method for lag time, 75, and so now it has the lag time up at the top. Once you type that in and click OK, so we have a couple of options to choose from. You can compute intensity, and so the SCS method was saying the time of concentration would be 17 minutes. If we use the other approach and compute the intensity, it's saying 11 minutes, and so of the two, it's more conservative if our design is based on the shorter time of concentration, because that's what leads to the higher rainfall intensity. So it's only done that for the first sub-basin, and we can do it for all of the others as well. We can compute based on either Manning's equation and the flow characteristics through the channel, or we could back out of that and go here into the basin data and choose which method we want it to estimate the travel time based on a curve number, and then get the rainfall intensity from that. So why is the intensity different for this one? It's all dependent on if you decide to assign different characteristics to each of the basins. And they have different sizes as well. So this basin that's the smallest could potentially have the highest intensity of them all because of its smaller size. The water is able to travel more quickly through it. So when you click on, you'll notice that it has a flow rate for each of them. And if I compute the hydrograph, then that puts it on top of the sub-basin in question. And there's also, you can bring up the menu to not just look at the basins, but you can also look at the outlets. And so the outlet is what's downstream of the basin, and so there's a way of combining the flow rates together that you could have a lag time that's having to do with the travel between watersheds. And so, for example, if there's a flow time through the stream that you want to account for, like this peak runoff is going to be at this outlet location, but then there's also a few minutes of travel time from when the flow gets from there to this outlet and where they're all combined together. So we'll talk more about lagging, but the 6C is where everything comes together, and so the total flow rate would be the sum of those three components. Alright, we're nearing the end of our available time, so let me just double check which additional tools I want to show you. We've looked at the help button, sub-basin delineation, so let me show you about trimming the digital elevation model. If we turn the DEM back on, you'll see that all those contours are there, and if we back out, there's quite a bit of extra elevation data that I don't necessarily need. I'm going to save this model for now, and so I only need the contours that are inside of my watershed. I don't need all of these other elevation data points. And so there's a way to trim that out. And if you move your cursor over here and right click, then trim is one of the options. And so right click on the digital elevation model, trim, and we're going to trim a polygon interactively, so click OK, and then what you do is you just kind of draw a shape around and encompassing your watershed, and then when you're done you double click, so click twice, and then it's trimmed out the elevation that you don't need anymore. So all that elevation data is still there, but what it's done is it's created a copy here that only has the stuff that I need. So what you could do is right click here and then delete the old layer, and if I save now, then the WMS file is going to be smaller than it was before, because now I've just only saved the elevation model that I actually need. You know, the contours that are outside our watershed of interest have kind of been jettisoned and deleted away. So that is the rational method. That is how you can subdivide the sub-basins. Are there any questions on what we went over today? Is there anything that I went through too quickly that you want to see demonstrated again before we finish for today's class? Sorry, James, I'm just now noticing your comment from earlier. Did you ever overcome the issue with Topaz? Because I can show you that. For okay, James fixed it. Good. Yeah, that has to do with defining the projection. So, I mean, that's an issue that probably everybody at some time or another is going to see, where if you don't have the same units for, if your projection units don't match what you have set in here in Topaz, then you'll get an error message. So, the projection units and the Topaz units are going to be the same. James asks, will the video be on YouTube? Yes, it will. Any other questions before we break for today? Let's just take one last look at these announcements. The homework assignment that has to do with you practicing these tools on a watershed of your choice, whether it's one of the ones I identify in the handout or one that you're particularly interested in locally. You can choose whichever you want, but you need to put together a series of screenshots that just illustrates that you went through that process to show that to me, and then upload those screenshots to Blackboard. Any other questions? All right, so that's it for today. Thanks for joining. If anything comes up as you're working on the assignment, feel free to send me an email, or we can have a chat over Zoom or Skype or however you like. So have a good day, everyone. I'll see you later.